Without further ado, let me mute myself as well here. This is David. He'll tell you a bit about himself, I hope. But something to know about David, he actually did this presentation in one of our casual meetups at Aerorust. Casual meetups are a thing that we started doing. I mentioned it in the beginning, just coming together and discussing topics. And I was very surprised when he wanted to do this talk. And of course, he proposed to do it here today in front of you. It did make he did made a lot of changes, and for the better. Believe me, I checked. And in general, he's a very active person in the community. So please, warm welcome to David.
Hi, hello. Thanks, Lacho, for introduction, for invitation, and yeah. So this talk, this presentation is a short story about how I spent weekend with IMU, which will be this talk will be just a shallow dive into embedded trust and sensors. So this is more technical presentation. There will be some code examples, but hopefully you won't. It won't be that scary. Uh, so yeah. So who am I? My name is Dawid Królak. I'm based in Łódź, Poland, and today I'm here. Unfortunately, only virtually, but maybe next year I will try to be on site. And well, I consider myself as a general purpose software engineer. So basically, programming is way of solving problems. It's language is just the addition. It's just a tool. And about a few years ago, I became the Rust enthusiast. I've learned about this programming language. It's really interesting. You should uh, check this because no matter what you do, web or embedded or blockchain, just it's everywhere nowadays. It can be everywhere. It's not everywhere yet, but hopefully soon it will take over the world. And also, I'm an amateur volleyball player, so yeah, some sport activities. If you are spending a lot of time in front of a screen, just take a walk, do some sport activity. It's really, I guess, it might be beneficial for for us as we are spending a lot of time with computers, just to get in touch with the real world. And uh, And also, I'm passionate about European space exploration and engineering programs. And being passionate about European is not easy this time, because if you compare it to the China, India, US space market, it's we are really we have a lot to do in this in this manner. However, I want to, because I'm passionate, I want to learn more about this. I want to learn how things works. And one of the way of learning how things work is to build something on my own. So I was thinking, where to start, what to choose. Obviously, as a one person, I won't build a satellite, I won't build a plane, but maybe I can start in some part of those systems. So maybe some rocket engines, maybe GPS, maybe recovery system, drones, avionics, batteries, etc., communication satellites. But in the end, I decided that I will try inertial measurement unit because it's small part, it's relatively easy, and it's doable in a weekend, over the weekend, Saturday, Sunday. It's just a good way to start. So, and important thing, I'm not an aerospace engineer. I'm working in a different domain, but hopefully one day we will see how it will go. But I'm learning about this. So let's back to the IMU. So what actually it is. So IMU is a device that measures and report forces acting on our device. So it provides some details about orientation. And knowing our orientation is important uh, because we need to know where we are facing, where we are looking at. If we, let's say, want to go somewhere, change our position, first we need to rotate. But to rotate, we need to know where we are looking at right now and where we want to rotate, where we want to end to start actually moving. Our body is doing this automatically. We are not feeling this, but devices like boxes, drones, and etc. They need. We have to provide those information. And if we add and if we want to measure position, then we are building inertial navigation system, and IMU is a part of this because we can, from some forces, we can guess where, how far we went in any direction. So yeah, so IMU in real life can look like the image on the left, which is some of the racket IMU, which is a big chunky piece of hardware, and can be also the smaller one, like the single sensor that you can embed into your drone project or any drone or any embedded project. But what data it's actually giving us? So IMU can report quaternions or Euler angles. And if you haven't heard about quaternions, if you will start doing stuff with attitude orientation, you will get to this term very soon. It's one of the foundation for the mathematics. And quaternions are it's a special number system. It's like complex numbers, but slightly more complex. However, those are preferred in advanced software because they are easy to calculate by matrices. So computers are really good at calculating matrices. And but on the other hand, it's a new concept that we have to learn. And we, we will leave it for now. It's not needed for a Hello World application. So we will go with Euler angles, which is just angles in radians or degrees. Slightly more difficult for calculation, but yeah, it's good enough for now. So in terms of angles, we have three angles that I guess you've heard already. It's yaw, pitch, and roll. So yaw is in this uh, uh, this axis, like the pitch is this, and roll is rotating. So it's pretty easy to think. And when we are coding this, when we are writing software for handling this, it's good to keep one order of those angles. And uh, the preferred one is yaw, pitch, and roll because it's easy to remember. If you think about what plane have to do during takeoff, it first has to yaw. So on the runway it's yaw. It's aiming towards the runway. Then it's pitching when it's starting, and then in the end it's rolling to fly to our destination. So yaw, pitch, and roll, and this is like the commonly used order. So yeah, so I know what I want to learn. I know some basics. I know where to start, but now I want to do something uh, actually actionable, some project to that makes me learn this idea. So I decided to go with a cube with real-time orientation. So this cube on the right is what I want to rotate, and what will reflect to my physical breadboard. So yeah, So let's start planning. So step by step, first is to find actually a MCU, some microcontroller, find some sensor, some breadboards, connect everything, write some firmware to upload to our board, then write frontend because I want to display this cube. And for because of time constraint, writing frontend and handling frontend is excluded from this talk because it's a beast of, of its own. If you think about, there is a rendering, OpenGL, WebGL, web servers, a lot. But so we will put it aside and assume that it's already there. And the last step is, of course, plug and play. So we are plugging and we are playing with it. So yeah, so let's start with hardware and software. So first, we have to find stuff. We have to find breadboard, Pico, sensors, etc. So each such project starts with diving into such boxes that you can see on the right and trying to find all the pieces of puzzle that further will be connected. And in my case, I found two breadboards, one Raspberry Pico, LSM3 or 3D, which provides me accelerometer and magnetometer. So this is 6 degrees of freedom sensor. Also, I found MPU 6050, which provides gyro plus accelerometer. So again, it's 6 degrees of freedom because each force we are measuring is in 3 degrees of freedom. So if we are measuring two forces, we have 6 degrees of freedom. And there are some sensors that provides 9 degrees of freedom. So it's like combined all three: accelerometer, magnetometer, and gyroscope. Yeah, another part is LED and resistor. And LED is just because sometimes it's nice to have some status, some feedback from the board, how it's working. So yeah, so I found the stuff and started connecting. So this is real life piece of board. It might not look very very appealing, but it's working. So that's good. And you can see here that I've decided to put sensors on the second breadboard, and this is because I might want to replace Pico with something different, with some different board, and then switching connection will make it easier. And yeah, so this is a cleaner view of connection. Here I decided to use I2C bus because it needs only two lines, and it can connect multiple sensors. So if I want to replace Pico with something different, I can easily detach I2C bus power and plug it to something different. So that's easy. All right, so we connected everything. Now start to code some firmware. And of course, I won't be doing live coding here. It's not the scope of this talk. But with Rust and Embassy, this is all we have to do to start to actually initialize our hardware. So our Pico hardware, our I2C, UART, and this is a way to go. So yeah, so let's connect the first sensor, which is MPU 6050. And this is very small sensor, but it's quite powerful. And this sensor provides gyroscope and accelerometer. There is already a crate, a library for this, for Rust, because in Rust libraries and drivers we call crates. So that there is a crate for this, so we can take something from of the shelf. And also MPU 6050 is interesting because it contains digital motion processor, which provides us easy way to go with calculating attitude. Actually, it's provides already attitude, because we can program this, we can upload firmware, and it will do everything for us. However, there are some drawbacks. First, that might be a licensing problem. So we have to check the license. There might, and it have to be uploaded. It have to be uploaded to the sensor. So it's like external binary blob, which is something. In some cases, it can be tricky. It wasn't tricky for my case, but it could be. However, we want to learn, so we are not going to use the digital motion processor. We will implement everything ourselves from scratch. So yeah, so gyroscope data, this is the first reading. So it reads angular velocity, degrees per second. Also, we need to read time between measurements, and we have to integrate those, and we should be ready to go. And here you might see the first problem. This is problem with frequency of receiving data. If you have low resolution of those data, we might get very inaccurate. We might be very inaccurate in our measurement. But yeah, let's try to do this anyway. So code might be a little bit scary. Hopefully it's not. But it's doing. But that's it. This is the whole Rust code that is needed for calculating this. It's just taking those three axes, x, y, z, calculate and multiply, sum, and send via UART so we can receive it. And when I connect it, it looks pretty nice. However, after a few seconds, it starts looking like this. Even without I wasn't moving it, it was just staying still. It wasn't. It's not reflect the reality. So there is something wrong with it, and I dig deeper, and the thing is, there is a drift. There is a low frequency drift noise, also called a drift, and as you can see in the column, those are measurement I've taken directly from the sensor. The numbers are going one way or another, so those are increasing or decreasing, and this is like not the perfect. So let's see if we can fix it. So we can fix it by adding accelerometer. So we can add measure forces, and accelerometer is using gravity to detect our orientation. So this is not detecting current change, detect current state, because the gravity is acting. Of course, it's not the perfect for satellites, as gravity is not acting, but on Earth it's sufficient. Also, we have to do some math, and with some math we have yaw and pitch. We don't have yaw, and this is because force is acting in this axis. So if we go like pitch, the force vectors are changing. If we are going this, vectors are changing. But if we are going uh, in this axis, in z-axis, there is no changes in force, so we cannot use it. Also, the other problem is noise. There is a high frequency noise in this sensor. So we have to filter this out somehow, because otherwise the image is shaky. The cube is shaking all the time. So again, we have some data, we have some measurement, not perfect, but let's see what we can see later. So let's connect second sensor, which is LSM303D, which is accelerometer and magnetometer. From this sensor, I've used only magnetometer because accelerometer data I've already taken from MPU. And also I wanted to do my own driver for this because I wanted to learn something new. And okay, I've learned how to write driver a few months back because I wanted to, and I wrote a driver for this. So I'm using here my own driver. However, if you want to write your own driver, this is you first place is a data feed that you want to check, and you are reading pages after pages after pages. Uh, However, those are the most important one pages because those contains register that you are writing and reading. So how to operate, how to actually write and read data from sensor. And I won't go through the uh, whole driver. It's just some code that is reading and writing to the I2C bus in a proper manner that we've read from the documentation. However, in Rust, there is some interesting thing because I2C is a bus and only one driver can own a bus. So this is like protecting us from reading and writing from random bus, especially using asynchronous code. So here we have, so here we need to somehow manage this. Rust provides some solutions for this. This is just a mutex, some synchronization primitives, some coding, some asynchronous mute, some synchronization structures that helps us to make it work, to share this bus to multiple sensors. So this is more or less like it should, like it looks like. So yeah, so we are adding magnetometer using custom driver. So we have yaw. So now we have X, Y, Z from gyroscope, which have its own problem. We have accelerometer X and Y from accelerometer, and we have Z from magnetometer. So we have like, so we can somehow combine those data. And yeah, with magnetometer, you can do yaw. However, magnetometer have this problem that it it measure magnetic field. So we have, so if you put some wire with flow with voltage, where there is some voltage, some current flow, then it will slightly rotate. And if you experiment yourself, you will see that it's small, but not noticeable. Okay, so we have all data. So now time to combine those measurements. And the term we are looking at is sensor fusion. It's combining all data from all sensors that we have into one single output. And it can be, in our case, is we have three inputs to the sensor fusion to calculate your pitch and roll. However, we can add the accelerometer from LSM 3 or 3D, and we can include this in sensor fusion as well. And of course, we can put all sensors that we want. The problem is how to make use of all those data and convert them into a single set of value. This yaw, pitch and roll, or in other examples, to quaternions. So this is what we are interested in. And here is interesting part, because when I've done this, I've noticed the one small problem with my code, that the cube wasn't rotating in a way I expected to. And I was trying to find out the problem, what's going on, and apparently the problem was because I haven't read all those letters, those printing on the sensor. Because if you look closely, on the left sensor, X is in this direction, and Y is in this direction, and Z is here. However, on the second sensor, the X is in this direction, and the Y is in this direction. So it's switched. So this is something you have to take care when you are connecting multiple sensors, that all are working within the same frame of reference. So okay, so let's back to our sensor fusion, data fusion. So when you start looking at something, when I start looking, there was I found a lot of answers that Kalman filter, Kalman filter, Kalman filter, complementary, Kalman filter, Kalman complementary, and I've decided to go with complementary filter as it sounds way easier to actually work with. So it was a good starting point. Kalman looks slightly more complicated, although I've figured this out somehow. But for sake of this presentation, I will stick to a complementary filter. So complementary filter is here we are getting some calculation from gyro. We are applying high pass filter. We are getting accelerometer and magnetometer. We are applying low pass filter, and we are merging. We are fusing those two data together. And this is the whole code for this filter. So as you can see, it's looks very easy, and it just works. Maybe it's not the best filter, but it works. However, there was another problem because when I started, the cube was because when I tilted, or it was tilted, the yaw angle was added, and again, it was why. And after some kind of digging, I learned that actually it makes sense that when we have the sensor, magnetic sensor, and we tilt it, the magnetic forces are slightly different. So it thinks it's rotating. So we have to compensate for this. So yeah, so we have to add tilt compensation, which is again a few lines of code, have some math operation. And after applying this, it started to work. So yeah, so now I prepared the demo. So we will see how it will looks like. So this is a prepared box. Hopefully you will see. Let me see if, yeah, so now you can see. Now I will try to share the second tab. So 1 second, please. So hopefully you can see right now, yes. And this is real live demo. So if I rotate it here, it's alive. And the tilt is correct. So yeah, so demo worked on conference live. Take it for a okay. So yeah, demo. So this is backup, but we've seen this is working, so we can move on. So is it end of a override or just the beginning? So let's see what I can learn more from this. So first, yeah, it's very far from real world application. I wouldn't put it to some drone or something and give it a try because it might not work pretty well. There are some edge cases that I found during testing and experimenting. However, it's a good platform for.
Can you just wait a bit and return a few slides because we missed the audio? Yes, from here. We need to fix it really quickly. Sorry
Demo.
about that. Okay, now we can hear you. Yes.
Okay, tilt compensation. It was presented. Can you hear me at this slide?
Yes, I think next one, just
Demo.
after the demo, go ahead.
Okay, after the demo.
After the demo, yes.
Okay, so is it end of the right or just the beginning? So obviously this is not a real world application. It's not ready. It's far. It's very far from the real world application. But it's a good platform for learning, I think, because it's from this point, I can go in many directions. Like I can, yeah, take care of some edge cases, detect them, and handle them, like negative angles. I can learn about different filters, maybe implement Kalman, maybe Madwig, Mahoney, etc. Some, uh, I don't know, maybe some machine learning, some AI stuff. Why not? I can work on math, use some matrices instead of derived equations. I can work on sending data transmission, how to compress data, how to send data more reliable with some checksums. Maybe replace RP my Pico with something more powerful like STM and RF. There's a lot of places. Maybe I can try to design my own head and design my own PCB, which contains all inputs for those sensors and for Pico. So this is like so here this story with IMU ends, but also begins a new journey here. And we will see where it will lead me. So yeah, so if you want to start learn about something, just pick something small, try, and trust me, you will learn a lot just trying to build it yourself. Yeah, that's it. So thank you. And are there any questions?
Thank you, David. Are there any questions? Yes, there is. Just a second. I'm getting there.
Hey, so I actually built the same thing like a couple of years ago. And the only difference was a different compass or magnetometer. And I was curious, what latency did you achieve after all the filtering? And also how many samples do you collect each second?
I think I have this on some another profiling. I have some. I will have to check this. I don't have this the number. So it's very slow. Computation is very slow. It's very fast. Computation here, the filtering is fast. The slowest part, in my case, is sending data via UART, and numbers I don't remember, and I don't have those on site. It was in the first version of presentation, but then I removed this because I didn't want to put too many numbers. Sorry, I
And
not answer.
you mentioned you had issues sending the data over the UART. Are you able to, so when you are reading the sensors, are you blocked from sending over the UART, or can you do the same, can you do both of them at the same time?
I'm using, even if I'm using asynchronous code using Embassy, I'm using only one core. So there is no such thing as sending and reading simultaneously. It's scheduler decide whether it reads or sends.
Well, there is, because I did it in my operating system. Okay, thank you.
Okay, I'm interested how you could do this on one core, but okay.
I can get you in touch with Georgi and to discuss this. Any other questions? First call, second call. So, okay, thank you, David. A round of applause for David.
Thanks.
And enjoy your evening. Thank you again for participating. And yeah, we'll keep in touch.
Thanks.
Bye bye.
See you soon. Bye bye.